Welcome to this explainer. When we think about modern data centers, our minds immediately go to endless blinking rows of servers, right? But behind all that computing power is a literal war, a relentless battle against heat. And the true frontline defender in that battle? Well, it's not some fancy microchip. It's a massive mechanical marvel called the evaporator. Today, we're going to break this down. We're going to provide a really detailed yet incredibly easy to understand explanation of what this machine actually is, how it works, and why it is absolutely crucial to the future of our technology.
Okay, let's dive into this. It's kind of the ultimate paradox, isn't it? You've got this sprawling facility stuffed with ultra-powerful processors that are literally roasting hot, running 24/7. But somehow, pumping through the veins of this boiling hot server farm is a continuous, endless supply of freezing cold water. Have you ever actually stopped to wonder where that cold water comes from? I mean, how do you reliably generate an ocean of cold right in the middle of an oven?
Well, here is our roadmap for today. We're going to start with the cooling starting point. Then we'll look at how the actual heat exchange works. After that, we'll explore the different types of evaporators, examine the fatal risk of freezing, and finally, end with a massive and honestly pretty surprising AI-era plot twist. Let's get right to it.
Section 1. The cooling starting point. This is where the magic happens.
The evaporator is absolutely the beating heart of the whole cooling process. It's the starting point, and actually, it's the ending point of the cycle too. I want you to picture it as a super active heat marketplace. The water that's been circulating out in the data center, absorbing all that intense heat from the servers, it arrives at the evaporator warm and just loaded with thermal energy. And in this marketplace, that water trades its heat away. It leaves completely transformed into what engineers call chilled water, ready to be sent right back to the servers.
Section 2. How heat exchange works. Let's look inside the tubes.
And this brilliantly illustrates the sheer magic of physical phase changes. There are 3 distinct steps happening all at once here. Step 1. That warm water returning from the servers enters the evaporator. But at the exact same time, a special chemical called a refrigerant comes in. Thanks to a little component called the expansion valve, this refrigerant enters as a freezing cold, low-pressure mist. It's almost like a spray. Step 2. Physics takes over. Heat always wants to move from a warmer area to a colder area. So the heat from the server water naturally jumps right through the metal piping directly into that freezing refrigerant mist. And step 3? Because that refrigerant has such an incredibly low boiling point, absorbing all that heat causes it to instantly boil and turn into a gas. Meanwhile, our water, having surrendered its heat, cools right down and becomes our chilled water. Boom! It's a perfect continuous thermodynamic trade.
Section 3. Types of evaporators, how we actually build the machines.
So in the world of data centers, 2 main architectures completely dominate the space, but one of them is the absolute heavyweight champion. First up, we have the flooded shell and tube type, or as it's known by its Korean engineering term, Man-ek-sik. Imagine a giant metal cylinder, that's the shell. Inside, you completely flood that shell with liquid refrigerant, and you submerge hundreds of tiny tubes carrying the server water inside it. Because the tubes are just entirely bathed in refrigerant, the heat exchange is incredibly efficient. No joke, this is the absolute gold standard for massive, hyperscale data centers. On the flip side, we have the direct expansion type, or Gun-sik. It's basically the exact reverse. The refrigerant runs inside the tubes, and the water is in the shell. It's just less efficient overall, so it's typically reserved for much smaller, precision cooling equipment.
But that highly efficient flooded shell and tube design, it does have a very specific mechanical quirk. Since you're dealing with a massive pool of boiling refrigerant, the lubricating oil from the system's compressor can actually accidentally mix in. And over time, it'll pool at the bottom of the shell. If you just leave it there, it completely ruins the efficiency. Because of that, these systems require a highly complex oil return system to actively pump that oil back out. What's super fascinating, though, is how modern data centers are solving this today. They are adopting these revolutionary magnetic-bearing chillers that literally float on magnets, meaning they don't use any oil at all. It is literally an engineer's dream pairing.
Section 4. The fatal risk, freezing. This is some high-stakes engineering. You really have to remember, the evaporator is literally the coldest point in the entire mechanical plant. If, for some reason, the pumps fail and the water stops flowing through those submerged tubes, you have a major crisis on your hands. Within seconds, that freezing liquid refrigerant will turn the stationary water into solid ice.
This fatal catastrophe of freezing, often called dongpa, is something engineers legitimately lose sleep over. Because what happens when water freezes? It expands. And when it expands inside tightly packed metal tubes, those tubes are going to violently burst. It's a catastrophic failure that destroys the whole system and literally risks bringing the entire data center to its knees.
So, the crucial point is how we prevent this from ever happening. Engineers definitely do not leave this to chance. They build this robust, multi-layered interlock defense system. They install flow switches to constantly verify that the water is actually moving. They use differential pressure gauges and highly sensitive antifreeze temperature sensors. If any of these sensors detect even a hint that the water flow has dropped or the temperature is dipping just a little too close to freezing, the system triggers an immediate forced shutdown of the massive compressor. It just kills the cooling cycle instantly to save the machine from destroying itself.
Section 5. The AI Era Plot Twist. We are changing the rules of cooling.
Now, what's really interesting about these numbers is this shockingly warm temperature range, 15 to 22 degrees Celsius. That's roughly 60 to 72 degrees Fahrenheit. For decades, the golden standard was to chill water down to a rigid, freezing cold 7 degrees Celsius. But today's ultra-dense AI servers, paired with new liquid cooling tech, they don't actually need ice-cold water anymore. They run so incredibly hot that supplying them with cool water at 15 to 22 degrees Celsius, which, let's be real, is essentially room temperature, is more than enough to absorb their heat.
And this seemingly simple change, it's an absolute game changer for thermodynamics. As the experts point out, by intentionally raising the target temperature of the chilled water inside the evaporator, you fundamentally change the math of the entire data center. Because the evaporator doesn't have to work nearly as hard to hit a freezing 7 degrees, the energy-hungry compressor doesn't have to compress the refrigerant as intensely. And that drastically slashes power consumption.
Let's see how this builds into a complete paradigm shift. Under the old traditional cooling model, fighting to get water all the way down to 7 degrees meant your compressors were just screaming at high load. They were consuming maximum electrical energy. But under this new AI-era cooling model, targeting 15 to 22 degrees means the compressor load is remarkably low. And even more importantly, it unlocks something the industry calls massive free cooling potential.
Free cooling is exactly what it sounds like. Think about it. If your target water temperature is now 20 degrees Celsius and it happens to be 10 degrees outside in the spring, autumn, or winter, you don't even need the refrigeration cycle. You can completely shut down those massive compressors and simply use the naturally cold outside air to cool the water returning to the evaporator. This causes the data center's power usage effectiveness, or PEU, to plummet down to near a perfect 1.0. You are essentially getting millions of dollars worth of cooling for absolutely free just by raising the evaporator's target temperature. How wild is that?
Which leaves us with a truly fascinating question to wrap up on. We've gone from chilling water to 7 degrees to 15 degrees to 22 degrees and beyond. As AI processors continue to evolve, running at higher and higher temperatures, and as the acceptable water temperatures in our evaporators keep rising right alongside them to meet them, will the ultimate hyperscale data center of the future even need a traditional mechanical chiller at all? Or will the outside air just be enough all year round? It's a remarkable thought, and it all revolves around that unsung hero we explored today, the evaporator. Thanks for joining me on this explainer. And hey, keep asking the big questions.